Okay, this is Chapter 3, Objective 4 Notes for AP Calc BC. And so what we're going to be looking at is concavity and points of inflection, which will, and then also what's called the second derivative test. So in general, whenever we're working with concavity and points of inflection, we're going to be working with the second derivative, okay? So we'll be working with f double prime to help us find that. We can also define it in terms of f prime as well. So we need to make sure that we can kind of hold on to a couple of different pieces to make sure that we understand that, okay? So mostly f double prime, but we'll also be looking at our f prime as well, all right? So for concave up, so our function is considered concave up if f prime is increasing. And so that is different than meaning that f prime is positive, right? F prime positive means that f is increasing, but if f is, or if f prime is increasing, then that means your derivative or your function is concave up. Okay, so just to make sure we understand that. So if f prime is positive, then that means that f is increasing. However, if f prime is increasing, then that means f is considered concave up. Okay, so we need to make sure we're using that language appropriately. So when we mean the function is increasing, we're going to be saying things like f prime is positive, greater than 0, above the x-axis, that sort of thing. But whenever we're talking about f prime increasing, so the derivative increasing, then our function is concave up. Okay. So specifically, so another way to say that is that if the second derivative is greater than 0, so if the second derivative is positive, then our function is considered concave up. So concave upward looks like the section of the graph that will be a positive parabola. So this whole graph here would be concave up. And that would be because the derivative or the slopes of the tangents are increasing in value, right? So the slopes of the tangent are increasing. That's what this means, f prime increasing. So if I were to look at the slope over here of that tangent line, it is negative, right? And then it is becoming less negative, so less negative, meaning it's increasing, right? And then it'll hit a 0, and then turn positive, and then more positive, and so on. So the slopes of these, so becoming less negative, so increasing, and the slopes of these becoming steeper, more positive, so increasing. Okay? So that would be concave up. However, if I were to look at a function like this, so something like this is not concave up everywhere, right? So not concave up everywhere. It would only be concave up somewhere in this section here, right? So as long as it has some portion of the graph that looks kind of like a positive parabola, then we would have a section that is considered concave up. So then concave downward is the flip side of that. So we know we have a function that is considered concave down if the derivative is decreasing, meaning the slopes, right, the slopes are decreasing in value. And so we can also look at that if f double prime is negative, less than 0, then that is another way for us to consider the function being concave down, right? So two different ways to define concavity, right? Both meaning the same, you know, getting to that same concept. So how can we define concavity is either through the first derivative or the second derivative, right? So we can define it two different ways. So concave down, right, if f prime is decreasing, or if f double prime is negative. And you need to know both of those definitions. So you cannot think of them as just one or the other. You need to know both of those, okay? So again, just like before, if we're saying that f prime is negative, then we are saying that the function is decreasing. That's something different, right? But if we were to say that f prime is decreasing, right, so now we're talking about the derivative decreasing, then we're saying that the function is concave down. Okay, so making sure we're tracking both of those thoughts. Okay, so concave down, right? Concave down. That is what concavity looks like when it's downwards. Okay, so like a negative parabola. So if I look at that first component, or first way we can find it, the derivative being decreasing. So if I look at a slope over here, that would be a positive slope. And then on this side over here, it's becoming less positive, right? Less steep. So less positive, less steep, and then hit 0. So it is a positive slope, and then a little less positive, a little less, well, 0 there maybe. So it is decreasing, right? The slopes are decreasing in value, and then it turns negative. So So from zero, positive to 0 to negative, and then even more negative. So the function's slopes, right, are decreasing, so f prime is decreasing. And so then we can also look at this as then, therefore the second derivative is less than 0. Okay? All right, so concave up. So this is kind of like a cup. So think of this as like a little cup, right, where you can put a little bit of water in there or something like that. And then so concave up like a cup, and then concave down like a frown. I'm sure you've heard that. You came out of AB. So up like a cup, down like a frown. All right, so we have to be able to figure out, well, where does it switch, right? Like if I look at this graph here, it starts out concave down and then turns to concave up. So we have to figure out, well, where the heck is that little switcheroo at? Where's that switcheroo at? And that would be at what we call the point of inflection, okay? So that point of inflection is what we're looking for, and that is the point at which the graph changes concavity if the tangent line to the graph exists at that point, okay? So it is where, so we're looking for where that point of inflection is, so we're looking for basically where that graph changes concavity. And that could occur where the second derivative is either 0 or is undefined. But it's really important for us to always make sure that there is an actual change in concavity there. All right. So let's go ahead and take a look at this first example. So we want to find the intervals of concavity and the points of inflection. So the first thing we need to do is we need to get to that second derivative, right? So that is our first step. Okay, so you're going to find f double prime, so meaning the second derivative, so that means you're going to have to take the derivative twice. And when we find f double prime, we are going to equal it to 0, but we're also going to look for where it might be undefined. Okay. All right, so this might be a good place for you to press pause and give those derivatives a whirl and see how you do. Okay. So I'm going to go ahead and do product rule here. So there's 1 and there's 2. So a little product rule. So I'm going to do 1 and then d2. And the derivative of x minus 4 is just 1. So I'm going to just put a 1 there. So 1 d2. And then plus 2. And then d1. Derivative of x is just 1x to the 0 or 1. And then I am going to clean this up just a tiny bit here, so I'm going to call that 3x, x minus 4 squared, plus x minus 4 cubed. So again, that's still just that first derivative. I now need to find the second derivative. All right, so I have to take this derivative again. So I'm going to do product rule here, so this will be 1 and 2. So f double prime. So I'm still just working on that first step, right? Okay, so we're going to do 1, and then d2, and the derivative of x minus 4 is just 1 again, so that will be just times 1. And now plus 2, and then d1. So this is just the 1 d2 plus 2 d1, and now I'm going to take that derivative, so that would be 3 x minus 4 squared, and then the derivative of x minus 4 is just 1. And then I'm going to simplify this just a little bit. So I can see that these are essentially the same, right? They're just, as far as commutative property goes, because that really is just 3x minus 4 squared, and that's just 3x minus 4 squared. So when I take my second derivative, I'm going to go ahead and multiply 3x and 2 together. And then I'm going to combine those, so that would be 3x minus 4 squared plus 3x minus 4 squared, so that would be 6x minus 4 squared. Still working on that step 1. Okay, so now I have to set it equal to 0. There's going to be no excluded values here because I don't have any fraction piece. So in order for me to set this equal to 0, I actually want to factor this just because I want to be able to use zero product property. So I'm going to look at this group right here and this group right here and see what do they have common and factor out those pieces that are common. So they both have a 6 and they both have an x minus 4. And so then when I factor 6 and x minus 4 out of here, I'll be left with an x. And when I factor a 6 and an x minus 4 out of here, I'll be left with just an x minus 4. And again, I want to equal that to 0. So still working on that step 1. It's a doozy. Okay, so we have 6 and x minus 4, and then I don't have anything to distribute on this first group here, so then I'm just going to combine like terms. So I'm just going to add the x's together. So 1x plus 1x is 2x, and then of course I have that minus 4. All right, almost done with step 1. Okay, so now 0 product property, so I'm going to equal each piece of these things to 0. So this doesn't have a variable in it, so it won't ever equal 0. And then x minus 4 equal to 0 would give me a value of 4. And then when I set 2x minus 4 equal to 0, I would add 4 divided by 2, so that would be a 2. Okay, so I didn't show the algebra there, but I'm sure you could probably take a moment, press pause, equal both of those to 0, and then figure out that piece. All right. So now I've found finally step 1. So now I'm moving on to step 2. So I'm going to do a number line sign analysis, but for the second derivative. Okay, so a lot like what we did in the previous objectives where we were doing the sign analysis, but for f prime, right? So then I'm going to go ahead and set up my number line, make sure I call that f double prime, right? Make sure I call that f double prime, and then put these values on, but put them on in order, right? 2 and then 4. And so now I'm going to take values under 2, between 2 and 4, and then greater than 4, and then we'll figure out are they positive or negative in value, okay? So I'm going to go ahead and, so a number smaller, thank you. So a number smaller than 2, so I'm going to pick 0 because, you know, that's a nice and lovely number. And then substitute it up into here and then determine if it's positive or negative. So 6 will be positive, of course. That's not going to change anything. And then 0 minus 4 would be negative. And then 2 times 0 minus 4 would also be negative. So that would give me a positive value. So any number under 2 would give me a positive value. And then now I'm going to pick a number between 2 and 4. So let's say pi. I'm going to pick pi. Just kidding. I'm going to pick 3. All right. So again, 6 will be positive, which isn't going to affect anything. 3 minus 4 would be negative. And then here I would get 6 minus 4, which would be positive. And a negative times a positive would be a negative value. And then finally, a number greater than 4. So we'll pick, say, e squared, or maybe just 5. Okay, so let's pick 5. So when I substitute in 5, I'll get 5 minus 4, which is a positive. And then 10 minus 4, which is also a positive, which would give me a positive value. Okay. All right, so now I am ready to make my conclusion. So once I do my sign analysis, I'm going to make my conclusion. Basically answer the question, right? So make a conclusion. So just going back to that the definition here, so whenever f double prime is greater than 0, that tells us that f is concave up, right? And if f double prime is less than 0, then f is concave down. And then finally, where we have that change in concavity, we would have our points of inflections, and I'm going to abbreviate that POIs. Okay? All right, so here is my conclusion. So I would say f is concave up, so f is concave up wherever f is f double prime is greater than 0, right? So f double prime is greater than 0. So that would be these two intervals right here. Okay, we're going to do open intervals. So we're going to say from negative infinity to 2, and then again from 4 to infinity. All right, so it's really the same exact process, right, as what you just did in the previous objectives with f prime. You're just now doing it for f double prime. So it's just telling you different information, but the method is the same, which is kind of lovely, right? So not learning anything new there. And then finally for concave down, where f double prime is less than 0 or negative, and that would be from 2 to 4. And then we would have points of inflection wherever there is a change in concavity. So the concavity changed from positive to negative here, and that was where f double prime was 0. So that would be at x is equal to 2, and then also from negative to positive, so at x equals 4. So now it does ask for the point of inflection, and x equals 2 and 4 are not points, so we should really find those corresponding y values, right? So I would figure out what is f of 2 by evaluating that into the original function, right? So that would be 2, and then 2 minus 4 is negative 2 cubed. Do some arithmetic here. What is that? Negative 16. And then f of 4. So that would be 4 times 0 cubed, which is 0. So then my points of inflection would be actually at 2, negative 16, and 4, comma 0. Okay? All right, so there is that. And then we have another piece to cover. So let's go ahead and do that. So the second derivative test is just an alternate way to find relative extrema. So sometimes people get a little bit confused here because they don't, they kind of get confused because it says second derivative test, so they think they're, you know, trying to answer something about concavity or things like that. So try to keep that in mind, that when we talk about our second derivative test, we're specifically, this is just an alternate method. To find relative extrema. So it's certainly something you should kind of have in your back pocket, but you already know one way to find a relative max and a min, so you know it's not the end of the world if you struggle with this or you just totally forget about it. But it is nice to have a couple different ways to solve, because sometimes one way is easier than the other, right? And so that's why it's nice to have a couple options, right? Similar to solving, you can solve by factoring, solve by quadratic formula, so on and so forth. But, you know, so this is just another way to find relative extrema. So don't be fooled by the fact that it says second derivative test and think it's only about, like, points of inflection, things like that. Okay. So you know that a relative extrema occurs when you have your slopes of your tangent line are 0 or undefined. So this is specifically, though, we're going to be working with only where you have that horizontal tangent, so your slopes are equal to 0. So that means your f prime is equal to 0. And then what you're then figuring out is, you know, is that horizontal tangent sitting on a section that is concave up or concave down, right? So that's what this is saying. So you're checking to see, is that horizontal tangent, right? So f prime equaling to 0, so that's a horizontal tangent. You want to know, is it resting on a section that is concave up, or is it resting on a section that's concave down, right? That's what you're checking for. So if that horizontal tangent is resting on a section that is concave up, so this is your concave up, there is your horizontal tangent, right? So if that horizontal tangent is resting on a section that's concave up, then it would be a relative minimum, right? So then if that horizontal tangent is resting on a section that is concave down, then you would have a relative maximum, okay? And then, boo, if you don't know if it's concave up or concave down, then the test fails. And typically that means that it is a POI, okay? Then not like guaranteed, but typically then you would have a POI at x equals c. Okay, so like that's not like the second derivative test is not guaranteeing that. So keep that in mind. Okay, so because what could happen is it could be a very stalled out graph where there's not a POI. It could be like a higher degree graph where really what's happening is, you know, it's kind of, you know, going dilly-dally, 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 ooh, flatten out, and then dilly-dally. So it doesn't actually change concavity, but it also doesn't tell you that it's a min or a max. So that's typically for your higher degree functions, okay? And then you can just use the first derivative test to kind of verify, like, was it a stall out or was it a POI? All right, so let's go ahead and take a look at this first example here. So our first step is to figure out where those horizontal tangents are. Okay, so that's our first step, figure out where are those horizontal tangents are. And then just a reminder, that is setting the derivative equal to 0. So this will not, we do not use the second derivative test if we are working with undefined values. Okay, so let's take that derivative. So then this would just be 12x cubed, and then minus 6x to the first, and then we would equal that to 0. So let's do some factoring, so I can take out a 6x, and that would give me 2x squared minus 1. Okay, and then from there I can equal to 0, so I would set 6x equal to 0. And then here, 2x squared minus 1 equal to 0. So I'm going to add 1, divide by 2. And then when I square root, that would be absolute value. So this would give me a positive and a negative version. So 1 over root 2 or 1 over root 2. So something like that. Okay, so that's our first step. And then our next step is now we need to determine, so this is where we have horizontal tangents, right? At 0, 1 over root 2, both positive and negative, so that's where the horizontal tangents are. And now we need to know, is that resting on a section that is concave up or down to help us make a conclusion, right? Is that resting on a section concave up or down? So then we're going to find f double prime and evaluate our x values. So those are our critical numbers. And we're really just finding the sign, so we don't have to know like positive, or we just need to know positive or negative. Okay, so let's go ahead and find f double prime though. So that would be 36x squared, and then minus 6. And then we're going to take each of these values, so 0, positive, and negative 1 root 2, and substitute it into here to determine, is this horizontal tangent resting on a section concave up or down? Okay, so we're going to do f double prime of 0. So that would be 0 minus 6, so that would be negative. I don't care that it's negative 6, I just care that it's negative. Okay? So if f double prime of 0 is negative, then, so the second derivative is negative, that means you're concave down where you had that horizontal tangent, right? So you have a horizontal tangent at 0, and that is a section that is concave down. So then what is our conclusion? So that means 0 is a relative maximum, right? 0 is a relative max. Okay. All right, and then we're going to evaluate at 1 over root 2. So I'm going to do positive 1 over root 2. And wish me luck on this mental math. Okay, so when I square that, that would give me 1/2. Half of 36 is 18, minus 6 would be 12, so positive. So then the second derivative is positive. So the second derivative is positive. That means I have a concave up section. And remember, this is where a horizontal tangent is, right? That's what the first derivative equaling 0 means. The slope is 0, meaning we have a horizontal tangent. Second derivative meaning positive, then we are concave up. So we are concave up, and we have a horizontal tangent. So therefore, we have a relative min at x equals positive 1 over root 2. And then I'm going to do the same thing again for that negative version. And then because I'm squaring that, even though this is negative, it's still going to turn positive. So then this should equal the same, because whether I evaluate x at positive 1 over root 2 or negative 1 over root 2, that squaring is going to force it positive. So then I know that it will be positive as well. And so then my conclusion would be at plus or minus 1 over root 2, I would have the same thing, which is a relative minimum. Okay? All right. So there you go. All right, so let's take a look at the very last problem here. So we want to figure out what can the graph look like given some clues here, right? Given some clues. So let's go ahead and take a look at each of these clues and see what the heck are they trying to tell us, right? What the heck are they trying to tell us? So for this one right here, when they're telling us that at x equals 2, at x equals 4, the y value is 0, those would be x-intercepts, right? X-intercepts there. So then this section here is telling me f prime of x is greater than 0. So the first derivative is positive, right? First derivative is positive whenever x is less than 3. So this is telling me where f is increasing, right? So f is increasing to the left of 3. Right? That's what that's telling me. So f prime greater than 0 means that f prime is positive, and if f prime is positive, that definition is f is increasing, okay, and then to the left of 3. F prime of 3 does not exist, so there is no defined slope at 3, right? So that means we're going to have some sort of sharp turn at f prime of 3, right? So that just means there's going to be a sharp turn here, or a cusp, you know, something like that. That's what that's telling me. And then right here, f prime of x is less than 0. So f prime of x is less than 0, so f prime is negative. So if f prime is negative, then f is decreasing. So f is decreasing. And then whenever x is greater than 3, so that would mean to the right of 3. And then finally, it's telling us f double prime of x is greater than 0. So f double prime of x is greater than 0. So that would mean that f double prime is positive, which would mean f is concave up, right, everywhere except for at 3. So f is concave up everywhere except at x equals 3, which makes sense because if f prime of 3 is not defined, f double prime of 3 certainly won't be either. All right, so when I go do this problem, it seems like the key values that I have for my x are 2, 4, and 3, right? So I'm going to go ahead and do a graph. There's my x and my y. And then I'm going to mark out 2, 3, and 4. So 2, 3, 4. Okay. So when I do these, so I have x-intercepts at 2 and 4, so 2 and 4. So when I do these graphs, I try to get my increasing and decreasing in before I do my concavity, okay? So I get that increasing, decreasing in just really lightly. So I know that I need to be increasing to the left of 3. So that means I have to intersect this point, and I have to be increasing to the left of 3. So to go through this point, am I going to go from above to below or below to above? And if I want to be increasing, I know that I need to, go, something like that. So I'm just doing a really kind of a light kind of, a line there just to a guideline. So I have like, okay, I got to do something that's going to go uphill. And then ignoring the sharp turn right now, and then now I know I need to be decreasing to the right of 3. So here's 3. I need to be decreasing to the right of 3, and I have to go through this point. So decreasing means I'm going to go downhill, and so in that change is going to occur up here somewhere at 3. So then I'm just going to kind of do a light line again, just to kind of get an idea of what's happening, right? So I know I need to be increasing, then decreasing, and then I'm going to erase those lines because that change is going to occur at 3. So I know I'm going to have a sharp turn at 3, so far I do, right? But then now I have to get my concavity in. So now I need to be concave up, right? I need to be concave up. So now what I need to decide is I have to put a bend on both of these lines to where I get that concave up form. And remember, this is what concave upwards look like, right? That's what it looks like. It doesn't mean that that is the only vision for concave up. So this is concave up as well. That's concave up as well. So as long as it's some portion of that parabola, then you have concave up. So if I need to be concave up, I have to put a bend on this line. So I need to decide, do I bend it like downwards, or do I bend it upwards? And I need to bend it upwards, so it should look something like that. So then when I do bend it upwards, so I'm just going to, just somewhere right here, it doesn't matter, that's just kind of a random spot. I'm just going to put a bend on the graph. So that would be a concave up section. And then I'm going to do the same thing over here. So it needs to be, either, rounded downwards or rounded upwards. And I know I need to be concave up, so I'm going to round it upwards. And so that would look something like that. Okay? And then this would be the graph of f. And that is that.